Good day, everyone. So this is just a continuation of Ma'am Abapo's report that talks about the elements of point set topology. Now let's start with 3.8, which is the Bolzano-Weierstrass theorem. So the definition of a bounded set. A set S in Rn is said to be bounded if it lies entirely within an n-ball B or AR for some R is greater than 0 and some A in Rn. Now, theorem 3.24, or the Bolzano-Weierstrass, if a bounded set S in Rn contains infinitely many points, then there is at least one point in Rn which is an accumulation point of S. Now, the proof. To help fix the ideas, we give the proof first for R to the power of 1. Since S is bounded, it lies in some interval negative A. At least one of the subintervals negative A, 0, or 0 and A contains an infinite subset of S. Call one such a subinterval A sub 1, B sub 1. Bisect A sub 1, B sub 1 and obtain a subinterval A sub 2, B sub 2 containing an infinite subset of S and continue this process. In this way of countable collection of intervals is obtained, the nth interval A sub n, B sub n being of length B sub n minus A sub n is equal to A over 2 to the power of n minus 1. Clearly, the sum of the left endpoints A sub n and the inf of the right endpoints B sub n must be equal, say, to x. Why are they equal? The point x will be an accumulation point of S because if R is any positive number, the interval A sub n, B sub n will be contained in Bxr as soon as n is large enough so that B sub n minus A sub n is less than R over 2. The interval Bxr contains a point of S distinct from x and hence x is an accumulation point of S. This proves the theorem for R to the power of 1. Observe that the accumulation point x may or may not belong to S. Next, we give the proof of Rn, which is n is greater than 1. By an extension of the ideas used in creating R to the power of 1, the reader may find it helpful to visualize the proof in R squared by referring to figure 3.1. Since S is bounded, S lies in some n-ball B, 0A. A is greater than 0 and therefore within the n-dimensional interval J sub 1 defined by the inequalities, x sub k is greater than or equal to negative A and less than or equal to A. Your k is 1 to n. Here, J sub 1 denotes the Cartesian product. J sub 1 is equal to I sub 1 to the power of 1 times I sub 2 to the power of 2 times up to I sub n to the power of 1. That is the set of points x sub 1 to x sub n, where your x sub k is in I sub k to the power of 1, and where each I sub k to the power of 1 is a one-dimensional interval, which is your x sub k is greater than or equal to negative A and less than or equal to A. Each interval I sub k to the power of 1 can be bisected to form two sub-intervals, I sub k 1 to the power of 1 and I sub k 2 to the power of 1 defined by the inequalities. So kindly look at the figure 3.1. So that's the figure 3.1. Next, we consider all possible Cartesian products of the form. Just look at the form and then where each k sub I is equal to 1 or 2. There are exactly 2 to the power of n such products, and of course each such product is an n-dimensional interval. The union of these 2 to the power of n intervals is the original J sub 1, which contains S, and hence at least one of the 2 to the power of n intervals in A must contain infinitely many points of S. One of these we denote by J sub 2, which can then be expressed as J sub 2 is equal to I sub 1 to the power of 2 I sub 2 squared times up to I sub n squared, where each I sub k squared is one of the subintervals of I sub k to the power of 1 of length A. We now proceed with J sub 2 as we did with J sub 1. Bisecting each interval I sub k squared and arriving at an n-dimensional interval J sub 3 containing an infinite subset of S. If we continue the process, we obtain a countable collection of n-dimensional intervals J sub 1, J sub 2, J sub 3, and so on, where the mth interval J sub m has the property that it contains an infinite subset of S and can be expressed in the form J sub m is equal to I sub 1 to the power of m, I sub 2 to the power of m, up to I sub n to the power of m, where I sub k to the power of m is a subset of I sub k to the power of 1. So in writing, we have I sub k to the power of m is equal to A sub k to the power of n, m, and B sub k to the power of m. We have B sub k to the power of m minus A sub k to the power of m is equal to A over 2 to the power of m minus 2, where your k is 1 to up to n. For each affixed k, the sum of all left endpoints A sub k to the power of m, where m is 1, 2, and so on, must therefore be equal to the inf of all right endpoints B sub k to the power of m, where m again is equal to 1, 2, and so on. And their common value we denote by t sub k. We now assert that the point P is equal to t sub 1, t sub 2 up to t sub n is an accumulation point of S. To say this, take any n ball b t r, the point t, of course, belongs to each of the intervals j sub 1, j sub 2, constructed above, and when m is such that a over 2 to the power of m minus 2, which is less than r over 2, this neighborhood will include j sub m. But since j sub m contains infinitely many points of S, so will be TR, which proves that it is indeed an accumulation point of S. Okay, so let's proceed to 3.9, which is the contour intersection theorem. As an application of the Bolzano-Weierstrass theorem, we prove the contour intersection theorem. Theorem 3.25, let Q sub 1, Q sub 2, and so on be a countable collection of non-empty sets in Rn, such that first Q sub k plus 1 is a subset of Q sub k, where your k is equal to 1, 2, 3, and so on. Each set Q sub k is closed and Q sub 1 is bounded. Then the intersection k is equal intersection q sub k, where your k is equal to 1 up to positive infinity, is closed and non-empty. Now let's do the proving. So let S is equal to the intersection of your q sub k, which is your k is equal to 1 up to positive infinity. Then S is closed because of theorem 3.13. To show that S is non-empty, we exhibit a point x in S. We can assume that each q sub k contains infinitely many points. Otherwise, the proof is trivial. Now form a collection of distinct points A, which is equal to x sub 1, x sub 2, and so on, where your x sub k is in q sub k. Since A is an infinite set contained in the bounded set q sub 1, it has an accumulation point, say x. We shall show that x is in S by verifying that x is in q sub k for each k. It was suffice to show that x is an accumulation point of each q sub k. Since they are all closed sets, but every neighborhood of x contains infinitely many points of A, and since all, except possibly a finite number of the points of A, belongs to q sub k, this neighborhood also contains infinitely many points of q sub k. Therefore, x is an accumulation point of q sub k, and the theorem is proved. And then we have the Lindelof-Cavray theorem. In this section, we introduce the concept of a covering of a set and prove the Lindelof-Cavray theorem. The usefulness of this concept will become apparent in some of the later work. Now, what is the definition of a covering? A collection F of sets is said to be a covering of a given set of S if S is a subset of the union of A, which A is a subset of F. The collection F is also said to cover S. If F is a collection of open sets, then F is called an open covering of S. Examples: the collection of all intervals of the form 1 over n, or your x is greater than 1 over n and less than 2 over n, which your n equals to 2, 3, 4, and so on, is an open covering of the interval x, which is greater than 0 and less than 1. This is an example of a countable covering. Second example, we have the real line r to the power of 1 is covered by the collection of all open intervals a, b. This covering is not countable. However, it contains a countable covering of r to the power of 1, namely, all intervals of the form n plus 2, where n runs through the integers. Another example, we have let S is equal to x and y, where your x is greater than 0 and y is also greater than 0. The collection F of all circular disks with centers at xx and with the radius x, where x is greater than 0, is a covering of S. This covering is not countable. However, it contains a countable covering of S, namely all those disks in which x is rational. Just see exercise 3.18. The Lindelof covering theorem states that every open covering of a set S in Rn contains a countable subcollection which also covers S. The proof makes use of the following preliminary result. We have the theorem 3.27. Let G is equal to A sub 1, A sub 2, and so on. Denote the countable collection of all n both having rational radii and centers at points with rational coordinates. Assume x is in R to the power of n, and let S be an open set in Rn which contains x. Then at least one of the n balls in G contains x and is contained in S. That is, we have your x is in A sub k, which is also a subset of S, for some A sub k in G. Now the proof is the collection G is countable because of theorem 2.27. If x is in Rn and if S is an open set of set containing x, then there is an n ball B, x in R, which is a subset of S. We shall find a point y in S with rational coordinates that is near x, and using this point as center. We'll then find a neighborhood in G which lies between B, x, R, and which contains x. We will write it as x is equal to x sub 1, x sub 2, and so on. And let y sub k be a rational number such that the absolute value of y sub k minus x sub k is less than r over 4n, for each k is equal to 1, 2, and up to n. Then your y sub x is less than or equal to y sub 1 minus x sub 1 plus y sub n minus x sub n is less than r over 4. Next, let q be a rational number such that R over 4 or Q is greater than R over 4 and less than R over 2. The X is in BYQ and BYQ is a subset of BXR and also a subset of S, but BYQ is in G, and hence the theorem is proved. So see figure 3.2 for situation in R squared. So can you see or can you look at the figure 3.2? We have another theorem. We have theorem 3.28 or the length of covering theorem. Assume A is a subset of Rn and let F be an open covering of A. Then there is a countable subcollection of F which also covers A. The proof is let G is equal to A sub 1, A sub 2, and so on. Denote the countable collection of all n balls having rational centers and rational radii. This set G will be used to help us extract a countable subcollection of F which covers A. Assume X is in A. Then there is an open set S in F such that X is in S. By theorem 3.27, there is an n ball A sub k in G such that your A sub k is in X, which is a subset of S. So there are, of course, infinitely many such A sub k corresponding to each S. But we choose only one of these. For example, the one of smallest index, say M is equal to M of X. Then we have X is in A sub M of X, which is a subset of S. The set of all n balls A sub M of X obtained as X varies over all elements of A is a countable collection of open sets which covers A. To get a countable subcollection of F which covers A, we simply correlate to each set A sub k of X one of the sets S of F which contain A sub k of X. So this completes the proof. Now we have 3.11, the hang-barrel covering theorem. The length of covering theorem states that from any open covering of an arbitrary set A in Rn, we can extract a countable covering. The hang-barrel theorem tells us that if, in addition, we know that A is closed and bounded, we can reduce the covering to a finite covering. The proof makes use of the contour intersection theorem. We have the theorem 3.29 or the hang-barrel. Let F be an open covering of a closed and bounded set A in R to the power of n. Then a finite subcollection of F also covers A. The proof is a countable subcollection of F, say I sub 1, I sub 2, and so on, covers A by theorem 3.28. So consider for M is greater than or equal to 1, the finite union or S sub M is equal to the union of I sub k, where your k is equal to 1 up to M. So this is open since it is the union of open sets. We shall show that for some value of M, the union S of M covers A. For this purpose, we consider the complement R to the power of n minus S sub M, which is closed. Define a countable collection of sets Q sub 1, Q sub 2, and so on as follows. Q sub 1 is equal to A, and for M is greater than 1, so you have Q sub M is equal to A intersection R n minus S sub M. That is, Q sub M consists of those points of A which lie outside of S sub M. If we can show that for some value of M, the set Q sub M is empty, then we will have shown that for this M, no point of A lies outside S sub M. In other words, we will have shown that some S sub M covers A. Now, observe the following properties of sets Q sub M. Each set Q sub M is closed since it is the intersection of the closed set A and the closed set R n minus S sub M. The sets Q sub M are decreasing since the S sub M are increasing, that is Q sub M plus 1 is a subset of Q sub M. The sets Q sub M being subsets of A are all bounded. Therefore, if no set Q sub M is empty, we can apply the contour intersection theorem to conclude that the intersection Q sub K, where your k is equal to 1 up to positive infinity, is also not empty. This means that there is some point in A which is in all the sets Q sub M, or what is the same thing outside all the sets S sub M. But this is impossible since your A is a subset of the union S sub k, where your k is equal to 1 to positive infinity. Therefore, some Q sub M must be empty, and this completes the proof. Now let's move to compactness in R to the power of n. We have just seen that if a set S in R to the power of n is closed and bounded, then any open covering of S can be reduced to a finite covering. It is natural to inquire whether there might be set other than closed and bounded sets which also have this property. Such sets will be called compact. Now, the definition of a compact set. A set S in R to the power of n is said to be compact if and only if every open covering of S contains a finite subcover, that is, a finite subcollection which also covers S. The hang-barrel theorem states that every closed and bounded set in R to the power of n is compact. Now we prove the converse result. Theorem 3.31, let S be a subset of R to the power of n. Then the following three statements are equivalent. First, we have S is compact. Second, S is closed and bounded. Third, we have every infinite subset of S has an accumulation point in S. The proof, as noted above, B implies A. If we prove that A implies B, that B implies C, and that C implies B, this will establish the equivalence of all three statements. Assume A holds. We shall prove first that S is bounded. Choose a point P in S. The collection of n balls B ek, k is equal to 1, 2, and so on, is an open covering of S. By compactness, a finite subcollection also covers S, and hence S is bounded. Next, we prove that S is closed. Suppose S is not closed, then there is an accumulation point Y of S such that Y is in S. If Y is not in S. If X is in S, let Rx is equal to x minus y over 2, each r sub x is positive since y is not in S, and the collection b, x, and r sub x such that your x is in S is an open covering of S. By compactness, a finite number of these neighborhoods cover S. Say we have S is a subset of your union B, x sub k, and r sub k, where your k is equal to 1, 2, p.